Hello everyone. In this video, we will see problems related to inverse trigonometric functions. The very first question is, the principal value of cos inverse of minus 1 by 2 is what? So we will assume first, let x is equal to cos inverse of minus 1 by 2. That means cos x is negative 1 by 2. That can be rewritten as minus cos x is equal to minus 1 by 2. We have a trigonometric identity which says cos of pi minus x is nothing but minus cos x. So we will be applying that here to rewrite this negative cos x as cos of pi minus x is equal to, sorry, here it is plus half, is equal to half. Now, half is, cos of pi by 3 is nothing but 1 by 2. So again, this will be equated to cos of pi by 3. That means now we can equate this with this. That means pi minus x is nothing but pi by 3. Pi minus x is nothing but pi by 3, or x is nothing but pi minus pi by 3, which is 3 pi minus pi by 3, or 2 pi by 3. So the value of x is 2 pi by 3. X is nothing but the original expression, which is cos inverse of negative 1 by 2. In this, we need to find the principal value of sine inverse of negative 1 by 2. So first of all, let x equal to sine inverse of minus 1 by 2, which means sine of x is negative 1 by 2, or we can write minus sine x is 1 by 2. Now, 1 by 2 can be written as sine of pi by 6. Further, we have sine function, that is sine of minus x is nothing but minus sine x. So that means this we can rewrite, this negative sine x can be rewritten as sine of minus x is equal to sine of pi by 6. That indicates that minus x is pi by 6, or x is minus pi by 6. So the principal value of sine inverse of negative 1 by 2 is minus pi by 6. The principal value of tan inverse of 1 by root 3 is what? Again, let x equal to tan inverse of 1 by root 3. That means tan x is 1 by root 3. And 1 by root 3 is nothing but tan of pi by 6. That means we can equate now this x and pi by 6. So the result is x is pi by 6, means the principal value of tan inverse of 1 by root 3 is pi by 6. In this question, we need to evaluate what is cos of tan inverse of x. So first of all, let us assume theta equal to tan inverse of x, which means tan theta is equal to x, or we can say tan square of theta is nothing but x square, or we can add both sides by 1 plus tan square theta is 1 plus x square, and 1 plus tan square theta is nothing but secant square theta, and that is 1 plus x square. Secant square theta is 1 by cos square theta, which is 1 plus x square. That means its reciprocal, which is cos square theta, is 1 divided by 1 plus x square. So we can write down cos theta as square root of 1 by 1 plus x square, or it is simply 1 divided by root of 1 plus x square. Now coming back to the original question, cos of tan inverse of x is nothing but, since we assumed tan inverse of x as theta, so it is nothing but cos theta, and cos theta just now we evaluated, it is 1 divided by square root of 1 plus x square. That is the result of this. This we need to evaluate the value of cos of sine inverse of 3 by 5 plus sine inverse of 5 by 13 is what? So to start with, let us assume let A equal to sine inverse of 3 by 5, which means sine A is nothing but 3 by 5. Similarly, let B equal to sine inverse of 5 by 13, which means sine of B is equal to 5 by 13. That means this question can be rewritten as cos of A plus B. Now, trigonometric identity is there, which is cos of A plus B is cos A cos B minus sine A sine B. So we are going to use that now. So for using that, we have here only values of sine A and sine B. We need to find out the values of cos A and cos B. Cos A, since we know sine square A plus cos square A, which is 1, that means cos square A is 1 minus of sine square A, or we can say cos A is square root of 1 minus of sine square A. Applying that, we have cos A will be 1 minus of 3 square by 5 square, which is 9 by 25 under root. If we evaluate this, we get 25 minus 9, which is 16. 16 by 25 under root, so it becomes 4 by 5. Similarly here, cos of B will be square root of 1 minus of 5 square, which is 25, 13 square, which is 169. If we evaluate that, we get 144 by 169 under root, which is 12 by 13. So now we can expand this cos A plus cos B. Therefore, cos A plus B is equal to cos A, which is 4 by 5, times cos B, which is 12 by 13, minus sin A, which is 3 by 5, times 5 by 13. This will be 12 into 4, 48 by 65, minus 15 by 65. If we evaluate that, we get 33 by 65. Here we prove that sine inverse of x plus cos inverse of x is pi by 2. So let us assume let A equal to sine inverse of x, which means sine A is equal to x. Let B is equal to cos inverse of x, which means cos B equal to x. Since both are equal to x, we can equate sine A is the same as cos B. Now, again, sine A is equal to, there is identity, trigonometric identity, which says sine of pi by 2 minus theta is nothing but cos theta. So we will apply that in the right hand side of this, which means right hand side can be rewritten as sine of pi by 2 minus b. So now we can equate this A and this to get what? To get A is equal to pi by 2 minus b, which means A plus b is pi by 2. Already we assumed A as sine inverse of x, B as cos inverse of x. So A plus B is nothing but your left hand side, and pi by 2 is nothing but your right hand side. Hence proved. So that is the solution for this particular problem. In this question, it says if sine inverse of x minus cos inverse of x is pi by 6, then x is equal to what? So let us write down the given expression first. Sine inverse of x minus cos inverse of x is pi by 6. Call it as equation 1. We had already seen one more expression, which is sine inverse of x plus cos inverse of x is pi by 2. Call that as second equation. Now, if we add this first and second equation, we get 2 times sine inverse of x minus cos inverse of x plus cos inverse of x gets cancelled. That will be equal to pi by 6 plus pi by 2. Now the LCM is 6, so we get pi plus 3 times pi, which is 4 pi by 6, or it is 2 pi by 3. That means our sine inverse of x will be 2 pi by 3 times 2, which will work out to pi by 3. Which means our sine of pi by 3 is x. So sine pi by 3 means it is sine 60. Sine 60 is nothing but root 3 by 2. So that is the solution for this particular problem. Here it is given, if sine inverse of x minus cos inverse of x is equal to pi by 3, then x is equal to what? We will consider the given expression as equation 1, and we had already seen one more expression, which is sine inverse of x plus cos inverse of x is pi by 2. Let us call this as second equation. Now, if we add this first equation and second equation, we get 2 times sine inverse of x is pi by 3 plus pi by 2. Now divide both sides by 2, we get, in left hand side it will be simply sine inverse of x since we are dividing it by 2. Right hand side, first one will become pi by 6, second one will become pi by 4. Which means our x is nothing but sine of pi by 6 plus pi by 4. Now, we will expand this, which means x is, this is like sine A plus sine of A plus B, which is nothing but sine A cos B plus cos A sine B. So that means our x will be sine pi by 6. Sine pi by 6 is nothing but sine 30. Sine 30 is 1 by 2. And then cos pi by 4 will be 1 by root 2. Cos pi by 6 is nothing but root 3 by 2. And sine pi by 4 is nothing but 1 by root 2. So we may notice the common denominator, which is 2 root 2. So it is 1 by 2 root 2 times 1 plus root 3. That is the value of x in this. This question, we need to prove that cos inverse of 4 by 5 plus tan inverse of 3 by 5 is equal to tan inverse of 27 by 11. So first, let us assume, let A equal to cos inverse of 4 by 5, which means cos A is 4 by 5. Similarly, let B is equal to tan inverse of 3 by 5, which means tan B is 3 by 5. Now we have an expression, trigonometric identity, which is tan of A plus B is equal to tan A plus tan B divided by 1 minus of tan A tan B. We will be using this expression subsequently. So I need even this cos A to be converted to tan. So how do I do that? First, I need to find out what is sine A. From this, I can say sine of A is square root of 1 minus of cos square A, which is square root of 1 minus of 4 square, which is 16, 5 square, which is 25, and that will be square root of 9 by 25, which will give you 3 by 5. So sine A is 3 by 5. Now, we also require tan A. Tan A is sine A by cos A. Sine A we already obtained as 3 by 5. Cos A is 4 by 5. That means tan A is 3 by 4. So now tan of A plus B is nothing but tan A, which is 3 by 4, plus tan B, which is 3 by 5, divided by 1 minus of 3 by 4 multiplied by 3 by 5. Here in the numerator, the LCM is 20. So this becomes 15 plus 12. And in the denominator, LCM is again 20. So 20 minus 9. So this will become now 27 divided by 11. That means our A plus B, this means that A plus B is tan inverse of 27 by 11. Already we assumed this A plus B is nothing but cos inverse of 4 by 5 plus tan inverse of 3 by 5, which is nothing but our left-hand side of the given expression in the question. And tan inverse of 27 by 11 is your right-hand side. So hence we have proved. So we say hence proved. In this, we need to prove that cos inverse of 4 by 5 plus cos inverse of 12 by 13 is equal to sine inverse of 56 by 65. So to start with, let us assume let A equal to cos inverse of 4 by 5, which means cos of A is 4 by 5, and then let B equal to cos inverse of 12 by 13, which means cos B is equal to 12 by 13. Now, we need to use a trigonometric identity, which is sine of, because right-hand side involves sine inverse. So I will be using sine of A plus B's trigonometric identity, which is sine A cos B plus cos A sine B. So if we use that, we require actually sine A, sine B values also. That will be evaluated from here. Sine A is equal to square root of 1 minus cos square A, which is 16 by 25. So the numerator becomes now 9 and denominator is 25, which means it is 3 by 5. Similarly here, sine B will be square root of 1 minus of 12 square, which is 144, 13 square, which is 169. So this will be square root of 25 by 169, which is 5 by 13. So now sine of A plus B is sine A, which is 3 by 5, plus cos B, which is 12 by 13, plus cos A, which is 4 by 5, times sine B, which is 5 by 13. Now if we add this, we get 36 by 65 here, and this is 20 by 65, which gives you 56 by 65. So therefore, our A plus B is nothing but sine inverse of 56 by 65. A plus B is nothing but our left hand side, because we consider this as A, this as B. So it is our left hand side. And sine inverse of 56 by 65 is our right hand side. Hence the proof. This we need to prove that sine inverse of 3 by 5 minus sine inverse of 8 by 17 equal to cos inverse of 84 by 85. Again, let capital A equal to sine inverse of 3 by 5, which means sine A is 3 by 5. Then similarly, B equal to sine inverse of 8 by 17, which means sine B is equal to 8 by 17. So we will be using, since here we have a negative sign in between and right hand side is involving cos inverse, so we will be using a trigonometric identity, which is cos of A minus B, which will be cos A cos B plus sine A sine B. So here we don't have cos values, so we'll evaluate it. So cos A equal to 1 minus of 3 square, which is 9, 5 square, which is 25, under root. So here we get 16 by 25 under root, which is 4 by 5. Similarly, this one, cos B will be square root of 1 minus of 8 square, which is 64, 17 square, which is 289, and that will give us 225 by 289 under root, which is 15 by 17. So therefore, our cos of A minus B will be cos A, which is 4 by 5, cos B, which is 15 by 17, plus sine A, which is 3 by 5, sine B, which is 8 by 17, and that will give you 60 by 5 into 17 is 85, plus 24 by 85. Again, this will be 84 by 85, which can be written now as, which implies that A minus B is cos inverse of 84 by 85. We may notice this A minus B is nothing but your left hand side. So this is nothing but your left hand side, and this cos inverse of 84 by 85 is your right hand side. Hence the proof. Hence the proof. This we need to prove that sine inverse of 4 by 5 plus sine inverse of 5 by 13 is sine inverse of 63 by 65. So let us assume, let A equal to sine inverse of 4 by 5, which means sine A equal to 4 by 5. Similarly, B is sine inverse of 5 by 13. If we assume, then sine B will be 5 by 13. So since the right hand side is having sine inverse, we'll be considering the trigonometric identity, which is sine of A plus B, which is sine A cos B plus cos A sine B. So we will be using this identity to solve this. So here we may notice that we require cos values. So this will give you cos of A is 1 minus of 4 square, which is 16, 5 square, which is 25, under root. So that will give you 25 minus 16, which is 9. So 3 by 5. This one cos B will be square root of 1 minus of 25 by 169, which is 144 by 169 square under root. So it is 12 by 13. So therefore, sine of A plus B is 3 by 5, which is sine A value. Cos B value is 12 by 13 plus cos A value, which is 3 by 5, sorry, this sine A value is 4 by 5, sorry. Here I wrote it as 3 by 5, which is wrong. So 4 by 5 multiplied by 12 by 13, and then plus 3 by 5, which is cos A value, multiplied by cosine B, which is 5 by 13. So this will be 48 by 65 plus 15 divided by 65. Adding the numerator, we get 63 by 65. So that is your sine A plus B, which means A plus B will be sine inverse of 63 by 65. A plus B is nothing but our left hand side. So this is left hand side, and sine inverse of 63 by 65 is your right hand side. Hence proved. In this, we need to show that tan inverse of 1 by 3 plus tan inverse of 1 by 5 is equal to tan inverse of 4 by 7. So let A equal to tan inverse of 1 by 3, which means tan A is 1 by 3. Similarly, let B equal to tan inverse of 1 by 5, which means tan B is 1 by 5. Now, since the right hand side is also involving tan inverse, and here in between there is a plus sign, so we will be using a trigonometric identity, which is tan of A plus B, which is tan A plus tan B divided by 1 minus of tan A tan B. We'll be using that. So if we use it, what do we get? Now tan of A plus B here will be tan A, which is 1 by 3, plus tan B, which is 1 by 5, divided by 1 minus of 1 by 3 into 1 by 5. Here the denominator is 1 minus of 1 by 15. Numerator's LCM is 15. So here you get 5 plus 3. So this you will get 8 by 15 divided by 14 by 15. That will result in 8 by 14. Both are divisible by 2. So 2 4s are 2 7s are, which means A plus B is tan inverse of 4 by 7. A plus B, we may notice it is nothing but our left hand side, and this one, tan inverse of 4 by 7 is nothing but our right hand side. Hence the proof, or I say hence proved. In this, we need to prove that tan inverse of 1 by 3 plus tan inverse of 1 by 5 plus tan inverse of 1 by 7 plus tan inverse of 1 by 8 is equal to pi by 4. So we will first consider, let A equal to tan inverse of 1 by 3, which means tan A is 1 by 3. Similarly, let B equal to tan inverse of 1 by 5, which means tan B is 1 by 5. Same way, C, we are going to consider tan inverse of 1 by 7. That means tan C is equal to 1 by 7. And let D equal to tan inverse of 1 by 8, which means tan D is 1 by 8. So that means we need to prove that A plus B plus C plus D is pi by 4. For doing that, we will consider the following trigonometric identity, which is tan of A plus B is equal to tan A plus tan B divided by 1 minus of tan A tan B. So here our tan A is nothing but 1 by 3. So this is our general formula. So I will now change this to 1 by 3 plus 1 by 5, because we assumed tan A and tan B as 1 by 3 and 1 by 5, minus of 1 by 3 multiplied by 1 by 5. So the denominator is 1 minus of 1 by 15. In numerator, the LCM is 15. So here we will have 5 plus 3. So this will become now 8 by 15 divided by, this is 14 by 15. Or I will say tan of A plus B is nothing but 8 by 14, which can be simplified as 2 4s are 8, 2 7s are 14. So tan of A plus B is 4 by 7. Now, let us say tan of C plus D. Same trigonometric identity, which is tan C plus tan D divided by 1 minus of tan C times tan D. That will be, tan C is what? Tan C is 1 by 7, tan D is 1 by 8. So 1 by 7 plus 1 by 8 divided by 1 minus of 1 by 7 into 1 by 8. That will give us 1 minus of 1 by 56. Here LCM is 56, so we will have 8 plus 7 in the numerator. So this will become now 15 by 56, and this is 55 by 56. So therefore, tan C plus D is nothing but 15 by 55. Let us simplify this. 5 3s are 15, 5 11s are 55. Now, if we consider let A plus B is equal to E, and let C plus D equal to F. So what we will do now? We will do now tan of tan of E plus F. So because we are assuming this, so that means here we will be proving, that is to prove that E plus F, because this is E, this is F, is equal to pi by 4. So let us proceed with that. E plus F is nothing but tan E plus tan F divided by 1 minus of tan E times tan F. So tan E is nothing but 4 by 7. So that here, let me write it here, which means tan E equal to 4 by 7. And here tan F equal to 3 by 11. So now we will substitute those 4 by 7 plus 3 by 11 divided by 1 minus of 4 by 7 times 3 by 11. So in the denominator, it is minus 12 by 77. Numerator, the LCM is 77. So here we get 44 plus 21. So that means our tan of E plus F is equal to, here it is 65 by 77 divided by 77 minus 12 is again 65 by 77. So we get the result as 1, which means E plus F is nothing but tan inverse of 1. Now tan inverse of 1 is nothing but pi by 4. So we proved now E plus F is equal to pi by 4. That is the result of this particular problem. This, we need to prove that tan inverse of 3 by 4 plus tan inverse of 3 by 5 minus tan inverse of 8 by 19 is equal to pi by 4. Again, let us assume A equal to tan inverse of 3 by 4. That means tan A is 3 by 4. Same way, let B equal to tan inverse of 3 by 5, which means tan B will be 3 by 5. Then let's consider C as tan inverse of 8 by 19, which means tan C will be 8 by 19. So based on this, we need to prove that. To prove now that A plus B minus C equal to pi by 4. That is what we are supposed to prove. So we'll be considering two trigonometric identities. One is tan of what we had seen in the previous problem. Tan of A plus B is equal to tan A plus tan B divided by 1 minus of tan A tan B. That is one trigonometric identity. Other one, what we are going to consider is tan of A minus B, because there is a negative also in between. For that reason, tan of A minus B will be tan A minus tan B divided by 1 plus tan A tan B. So that is what we are going to consider. So these two identities. So first of all, tan of A plus B is, here tan A is 3 by 4. So 3 by 4 plus tan B is 3 by 5 divided by 1 minus of tan A, that is 3 by 4, into tan B, which is 3 by 5. So that will, the denominator will be 1 minus of 9 by 20. Numerator's LCM is 20. So here we will have 15 and here we will have 12. So this will become 27 by 20 divided by 11 by 20. So that will give us 27 by 11. That is our tan A plus B. Now, we will now create tan of A plus B minus C. So together, I mean, already we have done this A plus B, so that is why we are writing it together. So this formula will become now tan of A plus B minus, I'm sorry, it should be, it should be minus tan of C divided by 1 minus of, so here it will be plus, isn't it? Yeah, here it is plus in the denominator. 1 plus tan of A plus B times tan of C. So this will be tan of A plus B, we know it is 27 by 11 minus tan of C. Tan of C is 8 by 19. 8 by 19, yeah. 8 by 19 divided by 1 plus 27 by 11 times 8 by 19. So which means our tan of A plus B minus C will become, LCM for the numerator is 11 and 19, it becomes 209. So here it is 27 into 19, you get 513. Here it is 88. Whole thing divided by 1 plus 27 into 8, it is 216. 11 into 19, it is 209. So that we will get 425 divided by 209. Here it is 209 plus 216 is again 425 by 209. So both numerator and denominator are same. So the result is 1, which means I will write A plus B minus C is nothing but tan inverse of 1. Tan inverse of 1 is pi by 4. Now a plus b minus c is pi by 4. That is what we are supposed to prove. A plus b minus c is pi by 4. Hence the proof. In this, we need to prove that tan inverse of 1 by 7 plus tan inverse of 1 by 13 is equal to tan inverse of 2 by 9. So let A equal to tan inverse of 1 by 7, which means tan A is 1 by 7, and let B equal to tan inverse of 1 by 13, which means tan B is 1 by 13. Now let us consider the trigonometric identity, which is tan of A plus B which is equal to tan A plus tan B divided by 1 minus of tan A tan B. That will be tan A, which is 1 by 7, tan B 1 by 13 divided by 1 minus of 1 by 7 times 1 by 13. So this will give us 1 minus of 1 by 91. Here LCM is 91. So here it is 13 plus 7. So we get 20 by 91 divided by 90 by 91. That means tan of A plus B is equal to 20 by 90, which is nothing but 2 by 9. That means tan inverse of 2 by 9 is A plus B. That is what we are supposed to prove, because we assumed this. This A plus B is nothing but tan inverse of 1 by 7, tan inverse of 1 by 3. Hence the proof. In this, we need to find the value of x if sine inverse of 6 by x plus sine inverse of 8 by x is equal to pi by 2. So again, let us consider A equal to sine inverse of 6 by x, which means sine A is 6 by x. Similarly, let B equal to sine inverse of 8 by 6, which means sine B is equal to 8 by 6. Now, we can rewrite, we have one trigonometric identity which says sine inverse of theta plus cos inverse of theta is nothing but pi by 2. So we will be using that particular identity. For using that, we need to find out this, this expression, or you can consider only one, means I can find out this sine B. From sine B, let me find out what is cos B. So cos of B will be then square root of 1 minus of sine square B. Sine square B means it is 64 by x square, or x square minus 64 by x square, which is nothing but root of x square minus 64 by x square. I'm sorry, by x, because square root of x square is x. Now, if this has to match, that means our, sine inverse of 6 by x, I can rewrite. Now they had given in the question as sine inverse of 6 by x, they give. Plus, I will write this cos inverse of this entire thing, root of x square minus 64 by x. I can equate this to pi by 2. Which means if these two should match, means then I am supposed to equate. This implies that 6 by x should be equal to x square minus 64 under root divided by x. Or I can simply write 6 is equal to root of x square minus 64. Now squaring on both sides, we get 36 equal to x square minus 64, which means x square is 100 or x is plus or minus 10. So that is the result for this particular problem. In this, we need to prove that 2 times tan inverse of x is equal to tan inverse of 2x divided by 1 minus of x square. First of all, let us assume let x equal to tan theta, which means tan inverse of x is equal to theta. So our LHS will be 2 times theta. Now let us proceed with RHS. I'll call this as equation 1. RHS, if I proceed, it is tan inverse of 2 times tan theta divided by 1 minus of x square, which is tan square of theta. Now we have a trigonometric identity which says tan of 2 theta is 2 times tan theta divided by 1 minus of tan square of theta. So if we use that identity here in this above, this will be nothing but tan inverse of tan of 2 theta. Tan inverse of tan 2 theta is nothing but 2 theta. Call this as equation 2. So we may notice 1 and 2 are same. Therefore, LHS is equal to RHS. Hence the proof. In this, we need to prove that 9 pi by 8 minus 9 by 4 sine inverse of 1 by 3 is equal to 9 by 4 sine inverse of 2 root 2 by 3. So from this, the above question can be modified that it is the same as to prove that what I will do, I will retain this 9 pi by 8 in the left hand side and take this 9 by 4 negative, whatever here given, this to the right hand side. It becomes positive 9 by 4 sine inverse of 1 by 3 plus 9 by 4 sine inverse of 2 root 2 by 3. So now this can be again rewritten as 9 by 8 equal to 9 by 4 is common. We can take it outside. So here you will have sine inverse of 1 by 3 plus sine inverse of 2 root 2 by 3. Now, both sides we can cancel 9 and both sides if I multiply by 4, I can say to prove that, or I will say that is to prove that if I multiply both sides by 4, in left hand side I will get pi by 2, in right hand side you are multiplying by 4, so 4 by 4 becomes 1. So you have to simply prove that sine inverse of 1 by 3 plus sine inverse of 2 root 2 by 3 is equal to pi by 2. That is what we have to prove. Now let capital A equal to sine inverse of 1 by 3, which means sine A is equal to 1 by 3. Then let B equal to sine inverse of 2 root 2 by 3, which means sine B is equal to 2 root 2 by 3. So from here, I can arrive at cos A. Cos A is nothing but square root of 1 minus of sine square A, which means 1 minus of 1 square by 3 square, 1 by 9 it becomes, or it is actually root of 8 by 9. Root of 8 is 2 root 2. Root of 9 is 3. So here sine A will be square root of 1 minus of 2 square is 4. Root 2 square is 2. divided by 9. So which is nothing but 1 minus of 8 by 9. 1 minus of 8 by 9 is 1 by 9. Root of 1 by 9 is 1 by 3. So we got cos A and sin A. Now let us consider the identity, trigonometric identity, which is sine of A plus B. Before that, let me write this. So once we assume this, we are supposed to prove that A plus B equal to pi by 2. That means to prove that A plus B equal to pi by 2. That is what we have to prove, because we have assumed this as A, this as B. Now let us use this trigonometric identity, which is sine of A plus B, which is equal to sine A cos B plus cos A sine B. We'll be using this identity now. So by using that, I can say sine of A plus B equal to sine of A plus B equal to sine A. Sine A is 1 by 3 multiplied by cos B. Sorry, here I should have written this as, I'm sorry, this as cos B. I wrote it wrongly. Yeah. So sine A cos B. Cos B is also 1 by 3. Plus cos A, which is 2 root 2 by 3. Sine B is also 2 root 2 by 3. So the first figure is 1 by 3 into 1 by 3 is 1 by 9 plus 2 into 2, 4, root 2 into root 2, 2, 3 into 3, 9. So we get ultimately 1 plus 8 by 9, which is nothing but 1. That means A plus B is equal to sine inverse of 1. Sine inverse of 1 is nothing but pi by 2. So we already had proved that A plus B is pi by 2.